One place life may be able to survive on Mars is near the polar ice caps. This may seem counterintuitive at first because life needs liquid water and the ambient temperature doesn't rise above zero. However, there can still be small bodies of liquid water resulting from localized heating effects. On Earth and Mars, dust particles settle on ice, which then gets heated as a result of being struck by sunlight. Sometimes, these dust particles are heated sufficiently to melt the ice, forming a small hole filled with meltwater. The surface of this hole will often freeze over while sunlight passes through the ice and continues to warm the dust particle. As a result, the water around the dust particle remains liquid, forming a cryoconite hole. These host self-contained microbial communities powered by sunlight. It may be that similar microhabitats provide Martian life with a refuge. In the mid-latitude regions of Mars, recent research has suggested that glaciers will sometimes release meltwater, which, if true, would provide microorganisms with a short yet recurring source of liquid water. Radar images from orbiters identified what appears to be a large lake beneath a south polar ice sheet. In order to remain liquid, the water in this lake has to be either hypersaline, with 40% of its weight being comprised of calcium perchlorate, or be heated from a geothermal source. If the latter is the case, this lake would be a suitable habitat for life, but recent analysis has indicated that this lake may instead be a layer of frozen clay. With any source of liquid water on Mars likely lasting for less than a day, with years in between, if any microorganism existed on the surface, it would have to be able to go dormant. On Earth, many microorganisms will produce dormant structures known as endospores, some of which are so hardy that they can even survive in the vacuum of space. The hyperligotrophic nature of the Martian surface implies that microorganisms would grow very slowly and would undergo many rounds of dormancy for every time they divided. Once every 3 years, Mars is covered in global dust storms, which would spread any spores across the planet. One might think that eventually a spore would be blown to a suitable habitat. However, it is estimated that a spore has a maximum duration on Mars of around 600,000 years, and to make matters worse, with liquid water available for such short durations, most of the microbes may not be able to repair damage due to radiation before they can go dormant again. This would mean that most cells would be unable to reproduce, causing the population to slowly decrease towards extinction. But there could still be events that lead to population booms of Martian cells. Mars undergoes ice ages once every 15 to 40 million years and experiences lava flows once every 2 to 8 million years, while meteorites fall regularly. These events would expose fresh rocks to the surface, and these rocks would have iron and sulfur minerals, which microorganisms could oxidize to power their metabolism, using either perchlorates or trace amounts of oxygen in the atmosphere as an electron acceptor. Given the combination of oligotrophy, aridity, cold temperatures, radiation, and toxicity, many astrobiologists have argued that the surface of Mars is uninhabitable. But if life did begin on Mars billions of years ago, it may have found a refuge deep underground as the surface became more desolate. At 5 kilometers deep, the average temperature of the crust rises to above freezing, and the porosity of the rocks is around 8%. This is comparable to the porosity of Earth's crust 1.8 kilometers deep, and life existing at this depth is well documented. While it is difficult to infer what is going on deep underground on Mars, oscillations have been detected in the magnetic field that may have been caused by a planet-wide subsurface saltwater reservoir. Here, reduced gases such as hydrogen from the mantle would mix with oxidized gases from the atmosphere, such as carbon dioxide. Subsurface microorganisms could utilize these gases to produce methane as an energy source. Seasonal fluctuations in methane have been observed, which may be due to the activity of a deep biosphere, although other explanations haven't been ruled out. Even though the surface of Mars is mostly geologically dead, the mantle is still convecting, and convection currents will cause different parts of the deep crust to heat up. This will in turn circulate metabolites, nutrients, and any possible organism deep underground. In order to better understand how life on Mars could cope with the conditions present, astrobiologists have studied microbial adaptations to arid, cold, and oligotrophic environments. One of these environments is the Atacama Desert of Chile, which is seen as an analog for the equatorial regions of Mars due to its high day-night temperature differences. The McMurdo Dry Valleys of Antarctica are used as an analog for the mid-latitude regions of Mars due to their proximity to glaciers. Subglacial lakes beneath the Antarctic ice sheet, such as Lake Don Juan and Lake Vostok, would have similar conditions to those that may exist beneath the southern ice sheet on Mars. Finally, subsurface ophiolites, or small pieces of oceanic crust buried deep underground, often host serpentinizing reactions, leading to conditions similar to those which may exist in any Martian deep biosphere. While these analogs may be similar to Mars in two or maybe three ways, they cannot replicate the low pressure and high radiation present on Mars, and as we've discussed before, it's likely that a combination of factors render some environments uninhabitable. If we wish to truly learn whether or not Mars is inhabited, we likely have to go there. For many years, scientists have pondered whether or not life exists on Mars. In 1877, the Italian astronomer Giovanni Schiaparelli looked at Mars through a telescope and thought he saw cannelle, the Italian word for channels. This was mistranslated into canals into English, leading many in the English-speaking world to think that Schiaparelli claimed to have seen canals built by a Martian civilization. However, it turned out that the channels he saw were in fact scratches on his telescope. But still, in the subsequent 88 years, many wondered if Mars had a thriving biosphere comparable to Earth. These hopes were dashed in 1965 when the probe Mariner 4 conducted a flyby of Mars, and the images it sent back showed a barren, desolate world. In 1971, the Mars 3 probe landed on the surface, but contact was lost 14.5 seconds after touchdown. In 1976, the Viking probes became the first to transmit images from the surface, and these paved the way for many of the missions being conducted on and around Mars to this day. Today, many probes are exploring Mars, some of which are looking for signs of life. The most recent arrival is Perseverance, which landed in 2021 and is carrying a spectrometer to detect organic molecules in rocks and soils. Perseverance is also equipped with X-rays to look for petrological signatures of life. Abnormal microscopic features in iron oxide, sulfate, or perchlorate-based minerals could indicate that either they were produced by microorganisms oxidizing another source material long ago, or have recently been used as an electron acceptor in microbial metabolism. The Mars Odyssey was launched in 2001 and uses radar to search for subsurface water. Another rover, Curiosity, is also using spectroscopy to detect organic and biomolecules, but this instrument shines a laser on an object of interest, breaking it down and using the resulting light emissions to determine its chemical composition. This allows Curiosity to analyze samples that it couldn't reach with its robotic arms. This instrument can also determine the elemental and isotopic composition of the surface of an object. While these probes have provided invaluable information about Mars, they have yet to answer some of the more long-standing questions about the red planet. In the next few years, there are a series of missions to Mars that have been planned. One of these is the Mars Sample Return mission. This probe will carry a rocket to Mars and land in the Jezero crater. Here, it will rendezvous with Perseverance, where the rover will load samples it collected to be launched back to Earth for further analysis. Similarly, the Tianwan-3 probe will be launched and land at a yet-to-be-determined location on Mars to collect soils and return them to Earth. A rover named Milos is intended to use fluorescence microscopy to look for life and carry out isochron dating of sediments. The Mars Orbiter 2 is is intended to use hyperspectral and panchromatic cameras to investigate the early evolution of the Martian crust. To facilitate future Mars missions, one of the objectives of the Artemis missions is to build infrastructure on the Moon as a way station. Although no mission has yet been planned, two environments that planetary scientists hope to explore with rovers are lava tubes and the polar ice caps. While we may get samples from Mars back to Earth in the next few years, can we send more than robots in the foreseeable future?